So looking at number 5, Carly, I already said I screwed up on the answer key because I forgot to change the numbers there. Hey, let's draw a free body diagram. What are the forces acting on this biker? Get the obvious one. Absolutely. Is the bike sinking into the ground like quicksand? Is it lifting into the air like Superman? So there must be another force in exactly the same magnitude, but in the opposite direction. It's a Newton's third law, reactive force. Okay, what force is that? Now, a couple of days ago, we said, well, it's the ground pushing up. But last class, we gave the force of a surface pushing back against you a special name. Remember what we called it? Okay, this is going to be the normal force, Fn. The normal force. Carly, what else? This question mentions another force. Which one? That's a speed. Another force. This question mentions another force. Which one? You mentioned it about 20 seconds ago. No. I said, does this question mention more than one force? And you said, yeah, it does. And I said, oh, what's the other force? So you ready, Carly? This question mentions another force. You can tell because it has the word force next to a number. Sorry? Which way do you think air drag would point? Can you give me in terms of left and right, please? Thank you. And they even told me how big it is. They said that it's 230 newtons. And then I underlined a word with you folks. Actually, 2 words. What 2 words did I underline? Constant speed. Why? If you're at a constant speed, what does that mean? No acceleration. Which means, by the way, this free body diagram is impossible. It must be wrong. Because I have unbalanced forces. Do I not? And if I have unbalanced forces, it must be accelerating. For me to have a constant speed, Carly, there must be a force to the right. Tell me when to stop drawing. Tell me when to stop. How do I know to stop exactly? Constant speed means it's exactly the same size as air drag. Yes? And do you know what force that is? That's the road pushing me forwards. Friction. Propulsion. The answer here is and the reason I know that is the 2 words, constant speed. The fact that they said constant speed means everything must be in balance, which means if 230 newtons is trying to slow me down, there better be 230 newtons trying to speed me up. And because they're in balance, I travel at a constant speed. Oh. If I have my tires apply a bigger force backwards against the road, then the road force will get slightly bigger and I'll accelerate. I'll be going faster. I'll be applying a bigger force than air resistance. But the problem with air resistance, Mark, air resistance is we're going to talk about it today as a matter of fact. It's a very complicated force because the faster you go, the bigger it gets. There's a reason we don't really study air resistance in high school physics. You've all stuck your hand out the window of a car. And you've noticed that as you go faster, what happens to the force that you feel on your hand? It gets bigger. And not only that, you've also probably noticed you can lower air resistance depending on the area that you expose. You've all done this little thing when you're driving in a car, right? You really, because it's such a changing force, just to analyze it, you really need calculus. Every so often, we'll analyze it in like a snapshot mode. We'll say, what is it right now? But if you really want it, because it changes, understand, as soon as air resistance gets bigger, it slows you down, but because you're slowing down, now air resistance just got smaller. Which means now it's not so small, so you can speed up again, which means air resistance just got bigger. It's a difficult force to really analyze. Carly, do you see why I said, though, this one's so easy that it's tough? If you see the free body diagram, it's hopefully obvious, I hope. Any others? There should have been. I'd love to do number 3. Number 3, I'm sneaking in some Physics 12. In Physics 12, often what I'll do is I'll give the kids what are called using principles of physics right to explain questions. Explain using principles of physics. It's left over from the old Physics 12 provincial exam. There used to actually be an essay question on every exam. By essay, I mean, Chris, don't write a paragraph. By essay, what they would say is a part B to a written question. They would say, okay, what if this was twice as big? Tell me what would happen and convince me using good physics. Or they would give you algebraic stuff like this. So Olivia, here's an algebraic question. Okay? It says, in the diagrams below, assume that force F is the only horizontal force on the block. Gotcha. If the first block accelerates at rate A, what would the second acceleration be? Now, Olivia, my math nerd heart would love to do these algebraically. But for you, here's what I would say. I would say make up reasonable numbers and follow it through. Here's what I mean. It says assume the force F. Let's pick a nice number for force F. How about 12? Why 12? Because lots of numbers go into 12. It's a little trick of the trade. 2, 3, 4, 6, those all go into 12. So I'm going to let this be 12 newtons. I just made that up. And I'm going to pick a nice mass for M as well. What's a nice number? How about 2? I stay away from ones because a 1, when you multiply, doesn't make a difference, and I might accidentally think something canceled when it didn't, so I'll almost never plug in a 1. But 2s, 5s, 10s, 12s, 3, those are my go-tos. So I'm going to let M be 2 kilograms. What's our equation? Force equals what times what? F equals ma. Yes? So in my first situation, Olivia, I've said that the force is 12, and I've said that the mass is 2. For that to be true, in that first situation, what must the acceleration be? Must be, based on these numbers that I've made up, mathematically, A must be 6 meters per second squared. Now, let's go to the right-hand diagram. What's the force in the right-hand diagram? Brad, still F, so still 12. Yes? Yeah. But what did they say the mass was in the right-hand diagram? So instead of 2, what would it be? This must be a mass of 4. Right? What would the acceleration be in the right-hand diagram? Got to be 3. Yes? Now here's the question. How are these numbers related? Oh, it looks like the acceleration gets divided by 2. See how we got that? Do you want to try the second one with this same trick on your own and see if you can figure it out? I'll do that. Otherwise, I'll happily go over it next class, okay? So again, I would probably let F be 12, M be 2, A is 6. Oh, 2F, I guess that's going to be 24. What would happen to your acceleration? Okay? I don't think I will give you stuff like, no, you know what? I take that back. I might give you an algebraic one on your test, but a little bit different. And again, you can always make up numbers. Any others? 7C. What does number 7 want us to find? Find the what? And we said that weight is not kilograms. Weight is the physics word for mg. So I'm going to write this. It wants us to find... That's weight. And they gave me the mass. This is also a situation, I think, where I screwed up and I put the wrong answer. Yeah, I'm sorry. That won't happen too often, but I'm trying to retype my handouts this year, and you guys are going to pay for my mistakes. I apologize. G on the Earth, 9.8, but Carly, hopefully you've learned enough science to know that as you go further and further and further and further away from the Earth, gravity gets weaker and weaker and weaker and weaker and weaker. And if you crunch the numbers, and you'll learn how to crunch those numbers after Christmas, you'll find that if you're 2,000 kilometers above the Earth, G up there is only about 5.7. So the answer is going to be 90 times 5.7, which apparently is not 456. Now, I have fixed it on my original. Apparently, it's, hello. 513 newtons? Yeah, sorry. I apologize. Any others? 9? I'd love to do number 9. And Dom, I'm thinking about liking number 9. I'm thinking about liking number 9. I'm really thinking about liking number 9. I'm thinking about liking number 9. It may show up. I'm debating it, and I'm about 60-40. First of all, hey, it's falling in rock climbing. That's kind of interesting. And by the way, what we're talking about in number 9 then is this. The rock climber is climbing with a slack rope. They slip, and the rope jerks them to a stop at the end. So I think there's 2 parts, Justice. There is the while you're falling, and then there's the jerking you to a stop. Is that okay? So the first thing, 9A, what does 9A, Dom, want me to find? You know what? I think I'm going to defic. I'm going to say, what else do I know? What's his distance? Don't say 10 because it's not. He's falling down. Did I say falling? Then I would also think you know A. Anybody here rock climb? I always should ask. I've had a couple over the years. Okay. I think, Dom, you know this too, do you not? If you're a rock climber and you fall, what's your initial velocity? Yeah, right? You slip, right? And they want us to find VF. So do we have an equation that has VF, VI, A, D, and that in it? Grant says, hey, Dueck, this one. Although, Grant, can I do this? And how would I get rid of a squared? Okay. So it's going to be the square root of 2 negative 9.8 negative 10. And I think it actually works out exactly even. I think it's the square root of 196 and it works out to exactly 14. Now that's the speed, which is what it wanted. What if I had said the velocity? You'd have to add, because your calculator isn't going to give you the negative. You'd have to, Jake, say, I know it's going down. I'm going to put the negative there just to remind myself it's going down, but it looks like in part A I asked for speed. Is that okay so far, Dom? That, to me, totally fair game. That's last unit. What does B want, Dom? That's a job for a free body diagram. There's the climber. And we're talking about when the rope jerks him to a stop, or her to a stop. What are the forces acting on this climber? Get the obvious one. Darn right. What else? The rope. Oh, wait a minute. We gave the force from a rope a special name. Do you remember? Tension. Now, before I draw tension, am I going to draw tension bigger, smaller, or the same size as gravity? Let's see if we can puzzle it out. Speaking of puzzles. So back to my question. Hey, is tension going to be bigger, smaller, or the same size? And how can you figure it out? Let's see. When the rope jerks him to a stop, what direction is he traveling? Down. Is he slowing down or speeding up when the rope jerks him to a stop? Here's my question. Which way is he accelerating when the rope jerks him to a stop? Up, which means what direction must my winner be? Up, which means, back to my question, am I going to draw tension bigger, smaller, or the same size? Got to be bigger. Which also, I think, then leads me to my equation, because B wants the equation. Who's winning? Who's losing? Hey, what's part C want? Oh, how would I get the T by itself in that equation? So I did this. It's going to be plus the mg and plus the ma, and I said, let's do a walk across my equation. Do I know the mass? Check. Do I know g? Check. Do I know the mass? Check. Do I know a? G? Oh. What does C want me to find, Dom? You said it already. Which is? Word that begins with the letter T. Okay, ready? What does C want me to find, Dom? But you know what I'm going to spend most of my time finding? Acceleration. Because that's what I need to find tension. Did I say find acceleration? Hey, what else do I know when the rope jerks him to a stop? Did I say stop? Oh, that tells me something. I know VF. What else do I know? I don't think they told me the distance. That's not that -10. That's in free fall. Oh, they told me time? How long? By the way, rock climbers' ropes are deliberately designed to be stretchy. Okay. Sorry? What's time? What's the time? 1.25 seconds? What else? Why do I know VI? Oh, is V initial when the rope jerks him to a stop going to be the same as V final of free fall? We've seen this happen a couple of times before where we had a two-part question and the final of one became the initial of the other. Hey, is there an equation that has A, VF, T, and VI in it? Can you get the A by itself? Yeah, I got that okay. Yeah, I got that. Yeah. So it's going to be 0 minus -14. I will have a minus minus, which is a plus. All over 1.25. And whatever you get there, I think, put it right there, Dom, and then it's plug and chug. Is that okay? Jordan, that's a tough question. But do you know why I'm sort of liking that question? I think that's the entire year so far in one question. Is there a free body diagram required? Yeah. Did we do winner minus loser? Yeah. Did we use VF squared equal stuff from last unit? Yeah. Did we also use VF equals VI plus A? Yeah. Holy smokes, that's a nice question now. And it's rock climbing, kind of interesting to me. At the same time, whew, that's a toughie. That's a toughie. So we'll see. Yeah, which I think is, I think here the answer is right, yeah? Yeah. Okay. Rock climbing. Any others? So, because next week we're going to be watching a movie, I'm going to really butch through today to see if I can get through the entire lesson, and then you can work. You probably won't get time to work on the homework today. Got a couple of cool videos for you, but we want to get through the whole lesson if we can today. So, can you get out? We left off with lesson 3, which was right here. We were looking at types of forces. Give me 1 second. So, looking at what we were looking at types of forces, we talked about gravity, and then we introduced this idea of a normal force. And key idea here, I'm going to be asking you questions with scales in them, and I convinced you, I hope, last day, Mark, that a scale does not measure mass, because you were doing deep knee bends and it was moving. Your mass wasn't changing. What does a scale measure? A scale measures how hard the ground pushes up against you. A scale measures normal force. A scale measures normal force. And this gives us to I like this question. Elevator questions. You're going to have 3 or 4 elevator questions on your test. So read along with me. It says this. A 72-kilogram man stands on a Newton scale in an elevator. By a Newton scale, I'm saying this is a physics scale, and rather than kilograms, it says in newtons, so we don't have to do any conversions. What does the scale read if the elevator is accelerating upwards at 3.2 meters per second squared? Cole, what's this question asking me to find?
What the scale reads?
No. That's what it says. What's it asking me to find? Ah. Okay, you see the 2-step process? Whenever it's talking about a scale, I'm saying, it's really wanting me to find the normal force. Is that all right? Okay. This is a job for a good free body diagram. Here's the person in the elevator. What are the forces acting on the person in the elevator? Get the obvious one. Okay, gravity down. Is this person sinking into the ground like quicksand? Are they flying into the air like Superman? No. So there must be at least some other force up. Which way is this person accelerating? According to up. So the winning force, the longer force, must be up. What force is that? The floor that they're standing on. What do we give the name to that their floor that they're standing on force? Fn. Can you write me my equation here? Who's winning? Who's losing? I think my equation is going to be Fn minus mg equals ma. Because that's the floor pushing him up, is it not? We said the floor or the surface pushing you up is called the normal force. Acceleration's an acceleration, not a force. Acceleration doesn't go on my free body diagram, but Olivia, the fact that they told me the acceleration was up told me to draw the normal force longer, right? Cole, what did you say this question's asking me to find? Not what the scale reads. Sorry? Get the normal force by itself. Yeah. I think the normal force is going to be ma plus mg. Did they tell me the mass? Yeah. Did they tell me A? 3.2. Did they tell me the mass? Yeah. G? 9.8. Why not negative 9.8? We said with our tug-of-war approach in this unit, we're going to decide which way is positive and which way is negative by our winner minus loser. So we're not actually going to put the negatives in for the variables. For last unit, we'll have to. For this unit, not so much, because we've got stuff moving all over the place. Hey, what is the normal force? 900 and what? Let's see. 72 times 3.2 plus 72 times 9.8. 936 sounds right to me. Now that's the scale if it measures, that's what the scale reads, the normal force. If it measures in newtons, how do you go back to kilograms? What if you want to find what the scale reads in kilograms? Take this number, still on your calculator, and divide by 9.8. Because scales are calibrated to times by 9.8 to give you an mg rating. So divide by 9.8. What would the scale read if it was in kilograms? What would it say? What is his real mass in kilograms? 72. What's the scale reading? Does this person feel heavier or lighter right now? Feels heavier. This is what you feel on the elevator when it shoots you up. You feel heavier, like you're being pressed into the seat. What you think of, Alex, as your weight is actually not mg. What you think of as your weight is actually the normal force. In fact, a nickname for the normal force is the apparent weight of an object, because what you think of as your weight is actually what you felt pushing up through your feet when you're standing and pushing up through your body when you're sitting. Say what? I'll go on a rant in a bit. Next one, B. Accelerating upwards at 2.5 meters per second squared. This is a job for a free body diagram. What are the forces acting on this person? Get the obvious one. Yep. Is this person in the elevator sinking into the ground like quicksand? Are they flying into the air like Superman? So there must be another force pointing up. Bigger, smaller, or the same size? Olivia, what direction is this elevator accelerating? So there has to be a bigger force upwards. What force, not accelerate, what force is that? It's the ground pushing up against this person's feet, but we've given that force a special name, Olivia. What have we called that force? That's the force that a surface exerts in response to an object pushing down on it. Who's winning? Who's losing, Dro? And that's going to equal MA. I can get the normal force by itself by plussing the normal force over, I think. Sorry, plussing the mg over. I'll get MA plus mg. Hey, Mr. Dueck, last time you wrote mg plus MA. Oh, no, I did write MA plus mg. You can write MA plus mg or mg plus MA. When you're adding, Brad, order doesn't matter. When you're subtracting, you got to be way more careful. 72 times 2.5 plus 72 times 9.8. Okay, let's see if I can just backspace and edit a little bit here. 2.5. Haha! Do you get 885.6? 880, let's say 6 newtons. Put your pencils down. I was marking provincial exams one year, back when there was Physics 12 provincial exams, and we had a question that said, find the normal force. And at the table that I was at, one of the markers started chuckling to himself, and he showed me what a kid had written. So the question said, find the normal force, and a kid had written, come on, pen. This would have been funner if my pen hadn't just glitched right now. So he'd written that. I have no FN clue. At least he knew what the normal force abbreviation was, but he still got 0 on the question, right? Pick your pencils up. Not really, because the provincials were worth 40% of your grade. It really wasn't that. It was funny, but anyway.
It's pretty awesome.
Hey, Chris, let's do C. Okay? Read C to me, please. Okay, this looks like a job for a free body diagram. What are the forces acting on this person, Chris? Get the obvious one.
Gravity.
Darn right. Is this person sinking into the ground like quicksand? Are they lifting into the air like Superman? So there must be some other force up. That's, by the way, what we're using is Newton's first law to figure that out. We're saying, what? Why? Which way is he accelerating? So you're saying I should exaggerate and draw the normal force shorter. So Chris, who would you say would be winning here? So my equation is going to look like this. Winner minus loser equals MA. Now the question asks what the scale reads, but what did we say a scale measures? So really we're trying to get that by itself. How can I get the Fn by itself here? What's right in front of the Fn, immediately in front of it? A minus. The easiest way to do these ones, Chris, and we're going to take a bold step, we're going to do 2 steps in one. The easiest way to do these when the normal force is negative is plus it to that side and at the same time minus that one to that side. Because in front of the MA there is a little visible plus sign. Can I do both those in one step? You're going to be okay? It's going to look like this. Gravity drops down like a domino. The minus MA ends up here, and the Fn ends up there. Did I lose you? Jake, you okay with that? Okay? We plussed it and we minused something else at the same time. Oh, I think now I can plug and chug. The normal force is going to be mg 72 times 9.8 minus 72 times 5.2. Wouldn't it be what? Sorry? No. We took care of all of that. We said for our winner minus loser approach, we'll never put negatives in for the actual values. We've taken care of all of that in a good free body diagram and then deciding who the winner is. Good question. Do you get 331.2? 331? What would the scale read in kilograms? Divide that by 9.8. This is how you go from newtons to kilograms. Do you get 33.8? So I'm going to write here, or 33.8 kilograms, because this question for part B did ask us in kilograms. Hey, would this person feel lighter or heavier? Way lighter. This is the feeling when the elevator goes down. Okay? You feel like you're going to fly out of your seat. Has your mass changed? Has gravity changed? So mg is still there. You guys think mg is your weight? No. That's actually your weight, but what you feel as your weight is the normal force. In fact, if you look both at this equation and this equation, if there's no acceleration, what are you all feeling as your normal force right now? Just plain old mg. Every one of you is feeling that. You're used to that. We don't mind increasing the normal force. We're fairly comfortable with that. Who's been on the elevator? What's scarier, on the way up or on the way down? I think for most kids, actually, it's on the way down. That's a much more uncomfortable feeling. You're not used to it. On the way up, increasing the normal force, you feel that every time you jump. You don't realize it, but what you're really doing is you're increasing the normal force so that you can get acceleration up. Very casual. On the way down, that is historically wired into us in millions of years of evolution back from the days when we slept in trees. If you feel your normal force decreasing, your body assumes you've fallen. And you get an adrenaline rush, and you grasp something instinctive. It's all hardwired into us. That's a tough one to overcome. Try D on your own. I'll do it up here. Let's see if we get the same thing. I'm going to freeze the screen so no one can just copy. Draw the free body diagram. Derive the equation. You're going to be tempted to take shortcuts, but the method that I'm showing you lets me give you all sorts of weird curveballs, and they should just fall apart nice and easy. You get an answer in the 400s, I hope. You get 438 newtons? Yeah? Got your calculator here?
Yeah.
Yeah? The one that I finally got you to buy?
I know, I always have one. It was fake.
Maybe get it out. In kilograms, if I wanted, I didn't ask that for this, but if I'd said in kilograms, the scale would read 44.7 kilograms, and this person would feel, this would be uncomfortably lighter. Both of these, especially in C, if you're accelerating down at 5.2, we are so uncomfortable with a lower normal force, almost every one of you would let out a shriek and grab something, because suddenly you'd feel half as heavy, or less than half as heavy. E. E. How is E different from D? I see a 3.72.
Constant.
You know, I think, Chris, if we were clever, we would do that, wouldn't we? Hey, let's do a good free body diagram. What are the forces acting on this person? Get the obvious one. Gravity down. Is this person sinking into the ground like quicksand? Are they lifting into the like Superman? They're standing in the elevator. So there must be a force up. Bigger, smaller, or the same size? Now, I heard some people say same size, and I heard some people say smaller. One of the reasons I like the tug of war approach is as long as you're careful, you can make a mistake and catch it. So let's assume, Zach, you saw the second word in the question. What's the second word in the question? And you said because it's downwards, you said, oh, I think gravity is winning. And so you mistakenly drew the normal force smaller, thinking, oh, gravity's winning. That's not the end of the world. Who did you think was winning? Incorrectly, but who did you think was winning? Gravity. So you would go like this. You would say, well, gravity minus normal force, winner minus loser, still works, equals ma. But as long as you caught, Jake, that it's constant speed or constant velocity, if it's a constant velocity, what does that mean? Ah, so you can go like this. A equals 0. Which really means you have this. Right? How would you get the Fn by itself? I think what you end up with is this, which tells you there is no winner. It tells you it's a tie. I would go back really quickly and I would say, you know what? I think I should have drawn my free body diagram. There, easy fix. The tie pops out of here as long as you're reasonably careful. There's room, Alex, to guess wrong and catch yourself. In fact, the other thing is, if you guess totally wrong, if you pick a winner and it's actually the loser, you'll get a negative acceleration if they haven't told you the acceleration, and that'll get your attention too, and you'll say, oh, wrong winner. What's the answer? 72 times 9.8. Sorry, what? Let's go to 3 sig figs, so 706, yeah? So, you don't realize how profound this question is. This led to one of Albert Einstein's thought experiments. He saw this and he said, hey, wait a minute. Suppose you're in an elevator with no windows. And let's imagine a perfect elevator in outer space. He said, if you're traveling at a constant speed, you can't tell. He said, the only way you can tell if you're moving at a constant speed is by observation. We have no experiment. There is no experiment in the universe that can prove that you're moving at a constant speed. You can detect acceleration. All of us have built-in accelerometers. They're backwards, but all of us have built-in accelerometers. But if I'm moving in outer space at a constant speed, the only way that I can tell if I'm moving is to observe something else and see if I'm moving relative to that object. That's why he calls it the theory of relativity. Okay. Started a little thinking here. Are you moving? Brad's wrong. He is moving at a constant speed. Why are all of us moving at a constant speed? Okay, you've been told the world spins. Prove it. The only way we can prove it is we see the sun go across, and for a while we thought it was the sun that was moving for thousands of years, and then eventually we clued in, actually no, the sun's standing still relative to us. We're spinning. Oh, not only is the Earth rotating, it's revolving. We're revolving around the sun. Oh, and not only that, Chris, the entire solar system is moving at a constant speed throughout the Milky Way. And not only that, the Milky Way itself, we're moving. But all of those movements, the only way we can detect them is we compare where we are to other stars, relative to other stars. There is no way to tell that you're moving at a constant speed if you're in a room that's closed with no windows? Can't tell. You can, again, Jake, as soon as the speed changes, I can feel that. But otherwise, I have no way of knowing. This then led Albert Einstein to start to think, well, if that's the case, maybe acceleration and gravity can sort of be treated the same way, and that led him to his bigger general theory of relativity. Nerd moment over. Let's keep going. F. Accelerating downwards at 9.8 meters per second squared in free fall. Hey, what do you think a scale would read then? 0 is correct. Prove it. This is a job for a free body diagram. What are the forces acting on this person? Get the obvious one. Gravity. What else? Now, you said there's no normal force. Let's guess wrong. Let's assume that there is a small normal force. Now, I'm pretty sure because we're accelerating downwards, gravity is the winner. Yes, so I'm going to make sure it's longer. Let's build my equation. I would say, well, okay, winner minus loser equals ma, right? And then I would get the normal force by itself. I would say, well, okay, we do that, we do that. I would say mg minus ma equals the normal force. Then I would plug in numbers. I would say, okay, so the normal force is going to be m, 72, g, 9.8, minus m, 72. And what's my acceleration according to this question? 9.8. Please, God, without using your calculator, Chris, without using your calculator and putting your phone away, what's 72 times 9.8? Take away 72 times 9.8. You've just proven that if you're accelerating down at negative 9.8 meters per second squared, you'll feel weightless. This is called apparent weightlessness. True weightlessness is when you're in outer space away from any planets and there's no gravity acting on you. Apparent weightlessness is there is gravity, you saw it in the free body diagram, but there's no normal force. The astronauts in the ISS are all apparently weightless. They're still close enough that Earth's gravity is measurable. It's there, but they're falling. They're in free fall. We'll talk about how that works, but that's why they float. Put your pencils down. Get the homework off somebody else. It's going to be some of the questions later on in this assignment, okay? So that's the normal force. Another force we've talked about a little bit, air resistance. Turn the page. Air resistance is the force of air molecules bumping into an object that's moving through the air. And Olivia, the force of air resistance is always in the opposite direction of motion. If you're moving to the left, air resistance is to the right. If you're moving up, air resistance is down. Okay? So I wrote down here, draw force diagrams for each of the following. We're talking about throwing a ball up in the air, and there's three situations. Situation A is while it's in my hand. Situation B is when it's left my hand on the way up. Situation C is on the way down. Oh, and it says include air resistance for B and C. So let's look at A. While I'm throwing a ball up, what are the forces acting on the ball? Let's draw a free body diagram. Get the obvious one. Jake, what's the obvious one? Okay, absolutely. Jake, watch, look up. When I do that, which way is the ball accelerating? So there has to be a bigger force up than gravity, yes? Probably way bigger. What force is that? You know what? It's my, we'll call it F hand. I had somebody the other day say, Mr. Dueck, couldn't I call that a normal force, sort of? Technically, Mark, a normal force is reserved for a dead, inanimate object surface applying a force. In fact, what you'll learn next year and later on, in fact, in this unit, we'd call this an applied force. The applied force is the outside force exerted by the human being that's part of the equation, part of the question, part of the situation. Hey, let's look at situation B. What are the forces acting on the ball? Get the obvious one. Gravity. And then what did it say that it wanted me to include? Which way is the ball traveling? So which way is air resistance? I'm going to put it right next to it. And air resistance is never that big, especially for a ball, which is pretty aerodynamic. There's two downwards forces. What about situation C? What are the forces acting on it when it's on the way down? Get the obvious ones. Gravity. What else? Which way? Yeah, there'll be a small amount of air resistance up. Now, I can affect or change that air resistance based on the shape of this object. In fact, a parachute is designed to make air resistance exactly equal gravity so that you stop accelerating, hopefully at a low enough speed that's survivable. I wrote down here in example 4b, in this middle situation, how the heck can the ball be rising if all the forces acting on it are downwards? Explain using good physics. How the heck can the ball be going up? My free body diagram has both forces going down. Zach, what about, you're right. First of all, what direction is the velocity of the ball? What direction is the acceleration? The velocity and acceleration have to be in the same direction? No. And you know what? That's what the key is acceleration. I would just say this. Come on, I want a lowercase a. Okay, you're going to capitalize it. I want a lowercase for my symbol for acceleration. There we go. A and V don't have to be in the same direction. Now, Zach, eventually, if you keep accelerating, your velocity will end up in the same direction as acceleration, because eventually you'll slow down, you'll come to a stop, and then you'll start going in the same direction. But yeah, there's no rule that says velocity and acceleration have to be in the same direction, but that's a common one. As a matter of fact, my physics 12s, I give them this same question, but instead of straight up, I have a cart that's been pushed up a hill. Someone gave the cart a big push, and it just continued coasting for a while, and all the kids want to draw a force on the cart pushing it up. No. No. But it's going up, Mr. No, the velocity is up, but I'm telling you its acceleration is down the hill because it's slowing down. Example 6 says, if the falling ball in example 4c is speeding up, write a net force equation. I'll scroll back. Here's my free body diagram. So example 4c, who's winning? Gravity. Who's losing? It would look like this. Gravity minus, how about F air for air resistance, equals ma. And if I knew more numbers, Kylie, I could probably do some good crunching. Oh, hey, parachuting. Parachuting.
Good morning, Pitt Middle Secondary. Today is our fruit and veg.
Back to here. Parachuting. A 90-kilogram parachutist, I mentioned that I jumped out of an airplane. A 90-kilogram parachutist free falls for a time and then opens a parachute. His new downward acceleration is now 1.5 meters per second squared. A says, compare the forces that act on the system. That's physics speak for draw a free body diagram, because that's really what you're doing. You're doing arrows and the lengths are comparing the forces. So let's do a good free body diagram. What are the forces acting on the parachutist? Get the obvious one. Gravity. Is this person in free fall? Nope. So I think there's some forces up. Am I going to draw the force up bigger, smaller, or the same size? How do I know? What force? You know what? Let's call that air resistance. I had somebody last day say, well, isn't it tension from the... It's technically tension from the ropes of the parachute, but Zach, it's the air resistance on the parachute. Okay? So we've done A. B. Write a force equation. Okay. What's the equation here going to be? Winner minus loser equals MA. That looks like the word fair. Let me move the air down a little bit so you can tell it's a subscript. There we go. By the way, another word for air resistance they'll often use is drag. So air resistance is also called drag. Hey, Brad, what's in front of the F air? No, right in front of it. Immediately in front of a minus. So I think to get the, because C says find the force of air resistance, I think what I'm going to do is I'm going to go plus that to that side whilst simultaneously minusing that to that side. You okay with it? By the way, the reason I always show that step, you can see it shows up an awful lot, and Alex, it's nice to be able to do that in one step and just get there. Yes? Yeah? Good, good. So, hey, Alex, what's my equation going to be? mg minus ma equals air resistance. Now, C said find air resistance. Double check. Did they give me the mass? Yeah. Did they give me G? And Carly, 9.8, not negative. Did they give me the mass? Yeah. Did they give me A? 1.5. And again, 9.8, not negative. I took care of all that, Carly, with my winner minus loser approach, which is kind of why I stole this, by the way, from a teacher at SRT named Mr. Kreitch, Brent Kreitch, very good physics teacher, and I really like this approach. You'll find if you take Physics 12, this will handle crazy, nasty stuff. All that happens, Sabrina, is your tug-of-war equation gets longer. In Physics 12, it'll be winner minus loser plus winner minus loser plus winner minus loser plus winner minus loser plus winner minus loser equals MA. But it's longer, not significantly tougher. And because it's all pluses and minuses, it's often really easy to get the stuff by itself, too, if you want to in the equation. Hey, let's crunch. What did I say the mass was? 90 and 1.5. 90, 9.8 minus 90, 1.5. $747 newtons. Okay. Eventually, Alex, I will slow down until I hit a constant speed. If I hit a constant speed, what would my acceleration be, folks? 0. What would air resistance be? Just mg. And the idea is then I'm no longer accelerating. The idea then, Jake, is I'm drifting down to the Earth, and hopefully that constant speed occurs at a velocity that I can survive the Earth's impact at. We have a special name for that. We call that terminal velocity. Terminal velocity without a parachute, you do also hit terminal velocity because your body has air resistance, but terminal velocity without a parachute, Jordan, is actually terminal. Like if you hit the ground, it's fatal. Okay? So I wrote down here on the next page, I went on a bit of a physics rant. I said, okay, the force of air resistance is actually not a constant value. The faster you go, the bigger air resistance. The smaller you go, the smaller air resistance. It's really a tricky, tricky force. And so I've gone on my rant already, but I'll say it again. Josh, I'm pretty sure you... Josh, yes? Hey, I got it. Getting it right. You really need calculus to analyze it properly. In fact, you won't. We barely touch on it in Physics 12. We look at it, and we can find it for specific situations like we've been doing here. But if you say, hey, what's the air resistance after 3 seconds? Yeah, it's a little tougher. Number 8 is kind of cool, but I'm going to pass because I've been talking like all class. I want to give you the homework, and you'll also get time to work on this next week. So what did I assign with my block G class? Good question. The homework is going to be skip 8 and skip 14. Skip 8 and skip 14. Let me draw that. Let me write that in here. So do number 1, 2, 3, 4, 5. No 6. Apparently I nuked that. 7. Skip 8. Try 9. Skip 14. You got about 10 minutes, and you also get some time next class as well.